Hi guys, welcome back to the channel. In this lecture, we are going to discuss about the equilibrium method or static method, which is basically used to calculate the collapse load of the structure. Okay, so in this lecture, we are going to discuss about equilibrium method, which is also known as static method. Okay. So before this lecture, in the last lecture, we have discussed about the incremental method. Okay. So in incremental method, what we studied about the sequence of plastic hinge formation. Sequence of plastic hinge formation and how much load is required for the formation of the first hinge, second hinge, and those things. Okay, and load required for the formation of first, second, third plastic hinge, right? So generally we don't require the sequence of hinges formation. Okay, so if you want, we generally want the collapse load of the for the structure. So if you want the collapse load of the structure only, collapse load of the structure. Okay, so we will not use this method, right? We will be using either equilibrium method or kinematic method. And kinematic method. Okay, so in this lecture we are going to study about the equilibrium method, and in the later classes we will be studying about the kinematic method. Okay, so this is the one drawback of the incremental method, is that this method is basically time consuming method. We already discussed that thing, right? Why it is time consuming? Because in this method we need to solve that indeterminate structure. Okay, and solving that indeterminate structure is quite a difficult task, right? So now let us start about the equilibrium method. Now, as the name suggests, the equilibrium method, here we'll be using some equilibrium conditions, okay, or you can say that the static method. Okay, so equilibrium condition are basically summation m equals to 0, summation fi 0, and summation fx 0, right? So in this equilibrium method, we will be using the concept of summation m equals to 0, right? We will be writing our equilibrium equation in terms of moment. In terms of moment, okay, right? So for the collapse of the structure, what three conditions we need to satisfy? One is equilibrium, okay. Second one is yield condition, and third one is mechanism. Okay. So in this method, we are using the concept of equilibrium condition. So this condition is automatically satisfied, right? Later we will be checking for the yield and mechanism to get the true collapse load. Okay. So for the true collapse load, these three conditions should be satisfied before the starting, just at the starting of the failure. Okay. So why it is called the equilibrium method or static method? Because here we will be writing the equilibrium conditions in terms of moment. Okay. So let us solve one problem on this topic, or equilibrium method, right? So now let us suppose I have one simply supported beam. Okay, and at the center one P load is acting, right? So this distance is L by 2, and this is L by 2. Okay. So if you draw the free body diagram using the equilibrium conditions, what is equilibrium condition? Summation Fy0 and summation Fx0. Okay. So reaction due to this P load at the support are P by 2. Here it is also, this is P by 2. Okay. So let us suppose I am writing the equilibrium equation for at this point for the center. Okay. For the center, let us, this is A point, this is C point, and this is B point. Okay. So at the center, if I write the moment using the equilibrium conditions, so MC will be P by 2 into L by 2. Okay. So this is through equilibrium only. Right? MC equals to P by 2 into L by 2. So here MC is equals to P L by 4. Right? So if the plastic moment capacity, of this beam is P and this cross section is constant, so I can write MC is equals to, so for this thing to be collapsed, okay, this thing we have write through the equilibrium condition, okay. For this thing to be collapsed, we need one plastic hinges because this is statically determinate structure. Okay. For statically determinate structure, we require only one plastic hinge. Okay. So the plastic hinge, and then we need to identify the location of the plastic hinge, where the plastic hinge will form. So plastic hinge will be formed under this point. Okay, because the ordinate of the moment is maximum at this point, right? So if you draw the bending moment diagram for this thing, it will look like this, PL by 4. So the moment is maximum under this at this C point. Okay. So for this thing to be collapsed, for the starting of the collapse, the MC value should be equals to MP value. Okay. So I can write MP equals to PL by 4. So if you write MP equals to PL by 4, from here, the collapse load PU will be equals to 4 MP by L. Okay, so this is the condition. So this is the value of the collapse load basically. So you can see that equilibrium condition is already satisfied because we have derived this equation through equilibrium only, right? So no need to check for the equilibrium in this method. If this is, and the bending moment diagram of this will be look like this. Here the moment is NP. So if you look at this bending moment diagram, you can see anywhere in this beam, moment is not crossing MP value. So M is always less than MP. Okay. So yield condition is also satisfied. Okay. Now only one plastic hinge is required for the collapse of this structure. So one plastic hinge is formed at this C point. So mechanism condition is also satisfied. So this is basically the true collapse load of the structure. Okay. Now one more thing I would like to discuss over here. We have write the equilibrium equation at this point C. Okay. So this equilibrium equation I can write anywhere in the beam. Let us suppose I am writing the equilibrium equation at this D point. Okay, and this D is L by 4. See this thing carefully. Okay, so if you write the equilibrium equation at this, writing equilibrium equation, because someone can ask why we are writing the equilibrium equation at the point C. Okay, so if you write the equilibrium equation at point D, so this will be, at this point the load is P by 2, so moment at MD will be P by 2 into L by 4, so this will be equals to PL by 8. Okay, so this thing is done. We have write the equilibrium equation. Okay, now next thing is to find the location of the plastic hinge. So plastic hinge will be formed at this C point, because that we can see from this moment diagram, maximum moment is coming at this point C. Okay, so the plastic moment, so this beam During the collapse, this beam will deflect like this. Okay, this is during the collapse. Actually, there will be some bending, but during the collapse, I'm just talking about during the collapse. It will deflect like this, right? So moment. So this is theta. This is theta. So MP is always opposite to this theta. So here this is MP, and here this will be MP. Okay. The purpose of MP is to restrict this theta value. Okay, that's why this is opposite to this theta. Okay. So if you draw the free body diagram of this thing, here one MP is acting. Okay, and one P load is also there. So you calculate RA from here, and here this is RA reaction will be there. Similarly, this is RB, and here the moment is MP. Okay, so RA will be RA into L by 2 equals to MP. RA equals to 2MP, right? So if you calculate the moment at point D, so at D, moment is MD is equals to 2MP into L by 4. So this will be MD is equals to MP by 2. Okay. So if you put this MP by 2 over here, this is MP equals to PL by 4. So PU will be 4MP by L. Okay. You can write equilibrium equation anywhere in this beam. The advantage of writing it under the C, because at C the plastic hinge formation is here. So we don't need to calculate these things. Okay. We'll simply equate that moment equals to plastic moment. That's why it is advantageous to write the equilibrium equation where the bending moment ordinate is maximum. Okay, because chances are there the plastic hinge will form at that point only. Okay, so if you write the equilibrium equation any other point, you don't need to solve this thing. Okay, you directly write MP equals to PL by 4. Okay, I think you need to see this thing very carefully. Okay, why we are writing just under the point C? We can write equilibrium equation at any point. Okay, that is the point of this discussion. Okay, so this is the case of simply supported beam. Now the important thing comes when the structure is little bit complicated, or you can say that indeterminate structure. So, for indeterminate structure, let us suppose first discuss the simple indeterminate structure, which is propped cantilever beam. Okay, this is propped at this end, right? And one load is acting at the center, which is P by 2, which is P. Okay, and you need to calculate the collapse load for this structure. The plastic moment capacity is PMC, plastic moment capacity is basically MP. Okay, and you need to calculate the collapse load for this structure, right? And this distance is basically L by 2 and L by 2. Okay, so this is a very important problem. It will give you basic idea how the static method or equilibrium method works in case of indeterminate structure. And this structure is basically indeterminate. Okay. So how much plastic hinges are required for the collapse of the structure? Basically 2 plastic hinges. 2 plastic hinges are required for collapse of this structure. Okay, 2 plastic hinges are required for the collapse of this structure, right? So we have idea where the plastic hinges will form, right? So first thing we need to discuss, we need to take some redundant over here, okay? Because static indeterminacy of this beam is 1, okay? And number of plastic hinges required for collapse equals to 1 plus 1, right? So basically that's why it is coming 2. So 2 plastic hinges basically required for the collapse. Now the important thing. if you want to solve this problem by static method or equilibrium method, first we need to take the redundant. Okay, select some redundant. And redundant we will be considering the moment. Okay, so now we know that generally the plastic hinge is formed at this point A. Let us suppose this is A point, this is B point, and this is C point. Okay, so for the crop cantilever, we know that the plastic hinge will form at this point and at this point. Okay, I'm not bothering about the sequence of plastic hinge, which plastic hinge will form first, which will second. Okay, and because we just need to calculate the collapse load. Okay. So the deflection during the collapse will look like this window. Okay. At this end, the moment direction will look like this, MA. Here the moment will be MC, and here the moment will be MC. You always take the direction of the moment opposite to this rotation. That's keep that thing in mind. Okay. So here you can see that this beam is deflecting like this. The direction of rotation is like this. Here the direction of rotation is like this. So moment will be opposite to this direction. Okay. So this is the thing. So now what we are doing is that I am considering MA as redundant over here. Taking MA as redundant. Okay. Now, if you are taking MA as a redundant, so first thing now we'll do, first we will draw the free bending moment diagram without considering redundant. Okay, so this structure will divide into two parts. One will look like this, and plus other will look like this. So the effect of these two structures will be same to this structure, right? Now we will be writing the equilibrium equation in terms of moment. That's why we are taking moment as a redundant, because we need to write equilibrium equation in terms of moment. Okay. So if you draw the free body diagram for this case, free bending moment diagram, it will look like this, and the maximum ordinate at the center is PL by 4. And I am considering this as positive. Okay, so this is basically sagging. So sagging, this upper side is compression, but downward side it will be tension. So this is basically a positive bending moment diagram, right? The deflection of this, it will deflect like this. Okay. Okay. So this moment diagram, if you draw the moment diagram for this thing, it will look like this. It will deflect basically like this. Okay, so this side is upper is this is basically hogging. Okay, so this is basically a negative bending moment diagram. This is positive bending moment diagram, right? So this thing you can get through the bending moment diagram also. Okay, this thing is easy to understand. Now we need to write the equilibrium equation. Okay, an equilibrium equation I just told you that write for the maximum where the maximum ordinate of the free BMD is there. Okay, so if you overlap these two things, okay, if you overlap, before overlapping, let us see this thing. Moment at this C point due to free bending moment diagram is PL by 4. Okay, moment due to this redundant at C is basically what? Minus, if you use the linear interpolation, so here the value is MA by 2. Okay, so this value is minus of MA by 2, right? So total moment at MC will be, MC is equals to PL by 4 minus of MA by 2. This thing should be clear. And this is what? Equilibrium equation. Equilibrium equation. Right? So if you calculate the moment at this point, this will be PL by 4. And then you need to subtract this thing because these two are opposite to each other. Okay, that's why this negative sign is there. So this is PL by 4. Net moment at C point will be PL by 4 minus MA. This is MA by 2. Okay, so this is basically our equilibrium condition. So that's why this method is called equilibrium method. Okay, first we have formed the equilibrium method. Then we will satisfy our mechanism condition and yield condition. Okay. So now, for the collapse of the structure, or you can say that if you combine these two bending moment diagrams, it will look like this basically. Okay. Right. So this is A point, this is C, and this is B point. If you combine these two bending moment diagrams, okay. So here this is negative, this is positive. These portions will cancel out each other. This portion. Okay. Now for the collapse of the structure, we need to have two plastic hinges, and the plastic hinge will form at this A point and this C point. Okay. We are not bothered about the sequence of plastic hinges because we just need to calculate the collapse load. Okay. Not any load which is first required to form the plastic hinge at A. What load is required to form the plastic hinge at C. We don't need that thing. Okay. So now we can see that the plastic hinge is forming at this A point and this C point. Okay. So at C, we can write MC is equals to MP. Okay. And if plastic hinge is forming at this A point, this MA will be equals to MP, and this MA by 2 will be equals to MP by 2, right? This again through linear interpolation. Okay, similar triangle concept if you use, you can at this point the moment will be MP by 2 clearly. So in this equation, if you put MC equals to MP, and this is PL by 4, this will be equals to MP by 2. So if you solve this equation, this will be 3MP by 2 equals to PL by 4. So this is 2. So PU is equals to 6MP by N. Okay. So PU is equals to 6MP by L. So this moment after the formation of plastic hinge, this is MP, and here also this portion is MP. Okay. So after the formation of the two plastic hinge, this structure will collapse, right? So equilibrium condition is satisfied because we have taken this equilibrium condition, equilibrium equation. Okay, it is already satisfied. Mechanism condition is satisfied. Two plastic hinges are formed. Now let us check about the yield condition. For the yield condition, we should draw the bending moment diagram at the collapse. Okay. So if you draw the bending moment diagram at the collapse, so it will look like this. Okay, here this value is MP, and here this value is MP. So you can see that anywhere in this beam, the moment value is always less than equals to MP. So yield condition is also satisfied. Okay guys, so in this problem I discussed how to solve this indeterminate structure using the equilibrium method, right? So here the indeterminate, there is only one static indeterminacy, so there is not much problem. But when there is 2 to 3 static indeterminacy is of 2 or 3 degrees, then there is little bit problem will be there. Not problem, our task is little bit difficult. Okay, so you can see that we have satisfied all the three conditions: equilibrium conditions, okay, mechanism conditions, and you can say that yield condition. So this is basically the true collapse load of this structure. This is true collapse load. Okay. So guys, if you have any doubt regarding this, if you find anything confusing while seeing this lecture, you can write in the comment section. Okay. how this direction of MP is decided, that thing you need to learn carefully. Okay. So guys, thank you very much. We'll meet in the next lecture.